so I'll give you a nickel. And I'm very grateful to have Nick Nelson here, who's initially wrangling the Zoom, but he's made me co-host because he has to duck out to wrangle family members, as I understand it. So we definitely understand that. And so if there's any delay in me wrangling the Zoom, please have pity on me. It's a real treat to have this webinar tonight. And I guess before I get any further, Nick, is there anything else you want to say about logistics before heading out?
The only thing that I should have told people beforehand, because I forgot, is that we will be recording this webinar. It's recording currently. And these will be posted for folks to watch after the fact. And amazing as it may be, actually, we get a lot of people watching these afterwards. So those will be available on the PICUP events tab.
Okay.
Okay, so, and I'm assuming once you drop out, Ernie will have the power to enable me to do the screen share.
Looks like I will, yes.
Okay.
So I'll actually turn that on right now, or at least I will try to. Okay. I think I have. And so just a couple of quick sentences of introduction. I do see familiar faces, but also some new faces, at least to me. And so welcome everybody to this PICUP webinar. And just here's the couple of sentences. So who are our speakers? Gautam Vemuri got his PhD at Georgia Tech, and he's an active researcher in intensity dynamics of semiconductor lasers, especially recently including controlling the characteristics of output pulses via coherence and interference effects. And you can imagine how that could lend itself to a lot of computational work. And certainly the dynamical systems is something that can certainly make it into computational physics courses. And in fact, Gautam has developed an intro computational physics course that he'll tell us about. Andy Gavrin got his PhD at Johns Hopkins University, and his research interests are physics education and magnetic materials, in particular nanostructured ferromagnets. He's an author of a book. He was the 2016 award winner of the David Halliday and Robert Resnick Award for Excellence in Undergraduate Physics Teaching from AAPT. And at least from my point of view, he played an important role in the undergraduate curriculum task force of the AAPT, which developed the AAPT recommendations for computational physics in the undergraduate curriculum. And so I've known Andy a very long time, and I'm just grateful to have done so. I'm also grateful to recently get to meet Gautam. Without any further ado, then I'll let the two principal speakers take it away, and I will be quiet. So take it away, gentlemen.
Okay, thanks very much, Ernie, for that. That was a great introduction, and also thanks just for the invitation overall to share what we've been doing. I'm going to go ahead and do the screen share and bring up our slides. Oh boy, okay. Let's see now. So I'm getting a message that Zoom will not be able to record the contents of my screen until I quit Zoom and then start over.
Try it now.
Okay, let's just try that again. Yeah, that's going to be better. I can see already that that's going to be better. There we go. I'm not sure what you needed to do there, but I'm glad you did it. Okay, so normalize. So oddly enough, the control bar is now covering the upper third of my slide, but I'll just make do. Our talk is about normalizing computation across the physics curriculum at IUPUI, and I want to start out, make sure I don't forget to thank our sponsors. We got our initial funding on campus from IUPUI's STEM Education, Innovation, and Research Institute. And subsequently, we're now funded by the National Science Foundation with an IU's grant. I want to explain first what I mean by normalizing. So what we want is for our students to consider computing to be a normal way of doing physics, just like they consider doing math to be a normal way of solving physics problems, or doing experiments to be a normal way of understanding what's going on. Excuse me. We want to put computation on the same footing as doing solving differential equations with a pencil or doing experiments. They should really view these things as complementary to one another, just as we view experiments and theory to be complementary in the past. And we want them to develop some judgment about what problems will be best solved analytically, what problems will be best solved computationally, and when to really merge those two techniques. If we can get them to that point, we'll have done our job. Whether or not, they're particularly brilliant programmers, that's not our focus. We're really trying to keep our focus on doing physics and understanding the world. And computation is a tool that they can use more or less skillfully. We hope more skillfully, but that's not the number one thing. We're not a computer science department. The other key phrase in our title was across the curriculum. And this goes a little bit to our process as we decided to get involved with this project. When we started out, there was sort of a grassroots desire to get more computation into the curriculum. We felt that we're all using computation in one way or another as professionals, and our students need to be trained to do the same. And one of the things we talked about was whether or not we wanted to have a few course sequence in computational physics that would be, maybe it would be required, or maybe it would be an option. And it was one of our earliest decisions that no, if we were going to make it normal, that meant it had to be everywhere. If we taught this using computational physics classes, that would automatically send a message that it's a separate thing, and that it's good for whatever problems the person who taught that course brought up, but maybe not for anything else. We wanted our students to really feel that computation is useful all across physics as a field. So we wanted to get computations into every course. We wanted students to see it all the time. We wanted them to take an increasingly sophisticated view of computation, just as they become more sophisticated in their use of mathematics as they progress, and in their ability to do experiments. And that's where we started using this phrase of making it normal. And that's really stuck with us and become kind of a watchword for this project. So I think at this point, I'm going to turn this over to Gautam for a bit, and he will take you through our department change process and a few other things.
Okay, so as Andy said, I'm going to talk about sort of some of the processes that our department undertook, because this is a department-wide effort. If you want every course to have some computation in it, excuse me, then we need buy-in from essentially every single faculty member. So there needs to be some sort of a shift in how the department approaches its curriculum and its teaching. Now there's quite a bit of literature on department change, here. So we went through some of it. We understood that there's no sort of one size fits all formula for this, and we have to kind of see what our local context is and what is it that we can do. So we are a somewhat small physics department. We have 10 tenure track faculty members, 3 lecturers. One of the things, or a couple of things that we had going for us in, Andy, if you could just stay on that slide. A couple of things we had going for us was that the faculty members are collegial with each other. It's not that we don't disagree, but it's just there's a culture of discussing things and sort of trying to see the other person's point of view. So if somebody wants to introduce some new methods of teaching, people will hear that out. And we've had a history of a commitment to pedagogical innovation. Andy Gavrin, many of you know him. Before that, Gregor Novak, a former faculty member who's since retired. They have brought about some changes. And so the faculty and the department was sort of used to this idea that there are lots of data-driven methods out there that one could use. Andy, if you could go to the next slide. So the effort in our department was a grassroots effort. This was a few faculty members thinking that introducing computations in the physics curriculum would be a good thing to do for our students. One of the things that this needs, in addition to this grassroots effort, is it needs leadership from the department chair. And so part of the reason I'm presenting this section, this department change section here today, is because Andy, who was the chair during the time that this was implemented, was our department chair. And knowing Andy as well as I do, I thought he would sort of underplay his role in describing to you what a pivotal role he had. And I think it's important that the department chair sort of be a champion for this and provide whatever support that the chair can. I speak from experience. I was the department chair before Andy, immediately preceding Andy. And in fact, during the time I was the chair,
my role model, that's what he's saying.
Well, so we actually introduced a computational physics course in the early 2000s. But that course was offered, I think, once or twice, and then other priorities took over. So much as, for example, I as a chair wanted to do this, it took almost 2 decades for us to really be able to do it. So even as we were discussing this in the department, this idea of introducing computations in the curriculum, there was lots of faculty meetings devoted to this. There were new ideas presented throughout. We were discussing various ways of doing this. Then, as you might imagine, there is some faculty resistance. And that resistance primarily centered around concerns over time management. This is, if a faculty member is used to teaching a certain course in a certain way, they have a certain amount of syllabus they want to cover. And then if you now have to add a computing element to the course, then how do I fit all this into the sort of the limited time I have? And most faculty members think they don't have enough time to cover what they're already trying to do. Another concern was a lack of computing fluency. People knew how to do computing for whatever research they were doing, but bringing it into the classroom and sort of weaving it into their pedagogy, people had some concerns. They had so there was a confidence issue which we had to work around. And then, of course, finally the workload, because this means coming up with new assignments. We have a goal of 25% of every course being computational, and having a computational part to it. This 25% is measured somewhat loosely. It could be 25% of the assignments, 25% of the grade. It's up to individual faculty members. But nonetheless, there was a concern that this would increase the workload for the instructors. So what we did was we had a couple of faculty members, and then of course Andy as the chair. We sat down with many of these faculty meetings and went over these concerns and tried to alleviate some of them. Then Andy sponsored, I think, 3 pairs of faculty members. So 6 faculty members attended the PICUP workshop in Wisconsin over a period of 3 years, 2 people each year. And this was very important for us. I think PICUP has played a very important role in our department being getting to the stage of having computations across the curriculum, because when our faculty members went to those PICUP workshops and they talked to other like-minded peers, they saw how, what sort of problems one can work with using computing, and just, discussing with peers. I think that was, and then the presentations at the workshop. So, so really PICUP was quite important for us. And then at some point, after several of our faculty members had attended the PICUP workshops, we requested PICUP to conduct a workshop within our department. So we had a few people. I see Kelly Roos is on here, and a few other people came to our department. There was a sort of a day-long PICUP workshop, which really then I think it was a very well done workshop, which sort of raised the enthusiasm level in the department and sort of motivated everybody to get on board. And then thanks to Andy's connections in the physics education community, we had, brought in several colloquium speakers as a part of our regular weekly colloquium series who talked about computing in the curriculum. And so we sort of, over a period of a year or maybe 2 or 3 years, sort of built up this excitement and this desire to do this and get everybody on board. Next slide, Andy. So once we decided we were going to do this, there were faculty discussions, and we sort of came to some general principles, among which were that we were really going to focus on physics and not coding. So we were not really that interested in how elegant the code is, or how efficiently it runs, how much memory it consumes, none of those things, because for some of these introductory physics and undergraduate physics things we're doing, these were not real limitations. So the idea was for the students to really focus on physics. We initially thought we would leave it up to individual faculty members as to what computing platform they would use. We were agnostic about it, but eventually that, after further discussions, we settled on MATLAB. It's freely available to our students. It's something that's used by engineers in the industry. So learning MATLAB and becoming familiar with it, we thought would be of benefit to our students. We decided, as Andy has said, to have a computing element in every course we teach. This is part of that normalizing the computing in the curriculum. To begin with, we decided that we were not going to have a course that is just focused on computing. So in other words, our early model from 20 years ago was we're going to have this one computational course, and then the other instructors would just pick it up from there. But after some discussions, we eventually decided to introduce an introductory course on MATLAB. And the motivation here was that since every course was going to use MATLAB, if the students early in their undergraduate career were exposed to MATLAB, how to get it on their computers, how, what the syntax is, and they have learned how to do some of the basic things, solving differential equations, numerical integrations, things of that sort. Then when they go into the subsequent more advanced courses, the instructors don't have to spend time getting the students acclimated to MATLAB. They can simply assume that the students have seen it before and sort of build on what the students have seen in that very first course on computational physics. We'll talk a little bit about evaluation at the end here, but we originally planned to use our usual end of the course instrument that we have and add some questions to it to evaluate the project. But eventually we developed our own survey instrument. And finally, one of the outcomes of this faculty discussions was that we should sort of review our curriculum and see what computational methods we want our students to learn, where in the curriculum do they appear, and so to sort of have a map, sort of have an idea of what it is that we want to do. And that map is on the next slide. It's here. This is not complete, but it just gives you a general idea. If the horizontal, the title in the horizontal direction are all the courses that we have for our majors in the department, and the vertical column is sort of the various topics that come up in these various courses. So for example, if you look at visualization, which is sort of in the middle of the table here, by visualization, we use it very broadly. It could be just as simple as plotting graphs. It could be something a little bit more sophisticated like animation. That sort of, some aspect of visualization one sees in every course. Similarly, numerical integration, comes up in a lot of different courses. On the other hand, you can see that it is just not complete because, for example, complex numbers, it doesn't appear under quantum mechanics. It's a bit hard to do quantum mechanics without complex numbers and phases and things of that sort. But nonetheless, this was sort of our, an attempt to capture what are the important computational methods which are listed vertically that we want our students, and in what courses do they appear, so that we can sort of sequence things in a way that students see, for example, they see matrices and how to work with matrices, how to do numerical integration early on, and then the subsequent courses would build on that. And then next slide, Andy. We came up with a set of student learning outcomes. We want our students to be able to apply, use computational tools to, for example, do matrix algebra, solve ordinary differential equations, Fourier transforms, numerical integration, so on. One of the things that we have been stressing in what we are doing is we really encourage the students to explore the physics. That, in other words, we assign a computational, whether it's a problem or an assignment or a project, and the code is working and they're getting the results that they expect. We sort of want them to think of that working code as the start of the process, not the end. We want them to use the code to investigate, other parameters, to test what the limits of validity of the code are, as well as what are the limits of the physical model that underlies whatever it is that they're doing. So we really want them to go beyond just, okay, I've done the assignment you asked me to do, my code works. No, so that's just the start. We want them to write clear code. So we tell them, look, it should be clear to another student, say the next year who comes into this course and wants to build on your code. We are trying to inculcate in the students the habit of testing their code by checking limiting cases, by comparing to known results. And so whenever there's a computational assignment, we tend to ask them, how do you know your results are correct? And it's a process, in the early courses, when they're sophomores, they don't know how to answer that. And then we sort of guide them through it, and then hopefully they get better as they go along. And finally, we ask them to write reports on the computational work that they're doing. We sort of try to stress that these reports should be written according to professional norms. Use LaTeX whenever possible to write their reports. So I'm going to now turn it back to Andy to talk about our evaluation instrument.
Okay, thanks, Gautam. And yeah, clearly we're just kind of hitting a couple of the high points here. So I wanted to skip to the evaluation because that really shows a little bit more of a window into what we've done and also into where we are and what we're learning as part of this process. So as Gautam mentioned earlier, we started out thinking that we would just kind of use the instructor-defined questions in the regular end-of-course surveys. It turned out really not to be productive doing it that way. We quickly found that we weren't able to understand anything about how our students were really learning and what whether they were finding computation to be normal doing it that way. So instead, we decided to build our own dedicated survey instrument, which, by the way, is now, I would say, pretty mature. And if anyone wants to borrow it, they're welcome to use it. I'll show you a little bit more detail about it later, but if you'd like a copy, I can certainly send it to you. So there are three major constructs in this survey. The first is a set of affect questions. We're really asking students about their attitudes about computation. And we built those questions to be the sort of things that we would say yes to. And then the question is, are students as enthusiastic about these things or see these tools the same way as we do? Then there's a section on self-efficacy. That is, we actually have that same set of techniques that was in the curriculum map that Gautam showed you a few slides ago. So everything from using LaTeX and using MATLAB as platforms to doing numerical integration, numerical differentiation, matrix operations, FFTs, a whole list of other things. And we ask them to rate their skills on those techniques. And then the last construct is that we ask students to say what they thought their initial abilities on those techniques were when they first started in the program. And I'll show you just a shred of data at the end here that suggests why we did that and what we hope to get out of that. So another of our big focuses is how this develops over time. So the way we do this is students take this survey at the end of every physics course, or at least we hope they do. It gets sent to them at the end of every semester where they take a physics course. If they're taking more than one course, they just fill it out once for the semester. But we want them to fill it out frequently throughout their curriculum. And our goal in the end is to be able to see at a course-by-course level when students' confidence with these various techniques rises. Right now, we haven't got enough data yet to look at it on a course-by-course basis. But what we can do is aggregate them at the 100 level, 200 level, 300 level, and 400 level, and see how the group is doing as they progress through those course levels. And I'll share some of that data in a moment. First, when you develop a survey, validity and reliability are some of the first questions you want to look at. We've taken the approach at the outset that we're going to establish content validity, which basically says, is the content connected to the constructs in the survey? So we started out with the project team writing this survey and saying, okay, we think these questions reflect students' attitudes and confidence with these techniques. Now we're going to hand it off to the rest of the faculty, and they're going to look it over and make suggestions to tighten it up a little bit. And then we went through a second round of going out to outside experts. And in fact, those were all PICUP people. So this is thank you number 2 to the PICUP community. I think about 5 people from PICUP looked at this survey and suggested slight rewordings and revisions and changing the order of the questions so that it really focused as well as it can on the constructs we're trying to measure. Then as far as reliability goes, the kind of gold standard is to have people take the same test multiple times and hopefully answer in the same way. That just seemed awkward in this case because we want them to take it multiple times as they learn. So asking them to take it multiple times without learning anything in between just seemed too awkward. So instead, we've taken the approach of doing split half reliability. So what we do is we say, all right, we've got these affect questions. We're going to analyze half of them, and then we're going to analyze the other half of them and use the Spearman-Brown mechanism to say whether or not those two halves are well correlated. And for the 3 constructs you can see here, these are all very good Spearman-Brown correlations. Anything over 0.8 is perfectly usable by most standards. So these are solid numbers. It's hard to get all the way up to 1, but given the size of sample we have, et cetera, this is solid. This is fine. So now I just want to look at, I think there are, like I said, 10 questions in each of the 2 self-efficacy sections, and I believe 5 or 6 in the affect section. I'm just going to give a couple of examples. So one of the questions in the affect sample is, it's a standard Likert scale type question. We ask students the extent to which they agree with this statement. Computational methods, experiments, and analytical solutions are equally necessary in the field of physics. And they choose, we have simply mapped strongly disagree to a 1 and strongly agree to a 5. And the bar graph on the lower right shows what the means and standard errors are for the groups of students by 100, 200, 300, 400 level. And now I want to thank our friends at the STEM Education and Innovation Research Institute. They have a research assistant, who I'll acknowledge by name later, who really helped us out with doing some of these statistics. They're helping us handle the data and satisfy our IRB as well by keeping these things anonymous, as anonymous as possible. So what they do is they start with an analysis of variance, looking at all 4 of those bins, and with a P of 0.001, they say, yeah, these things are different. Now let's look into the details. So then what we do is go into a pairwise comparison. And what we find is that 4 out of the 6 possible pairs among those 4 bins have statistically significant, at the P less than 0.05 level, difference. Now, p-values, I hope everybody has figured out by this point, all that says is this worth looking at or not? It really is not a measure of how strong a difference you're making. For that, you look at an effect size measure. And for reasons of, because basically we have significantly different numbers of students in each of these bins, way more students in the 100 level bin than in the 400 level bin, for instance, we use a Hedges G instead of a Cohen's D to characterize these effect sizes. For those of you who are familiar with these things, they're all scaled about the same way. So effect sizes in the 6 to 7 range are strong, and a 0.9 effect size is very strong. So basically what this data on the left is saying is that not only are these statistically significant differences, but they are comparatively large differences. Not much goes on between the 100 and 200 level. That's really just the introductory sequence playing out. But when students get up into the 300 and then the 400 level, the differences between those and the intro level courses are unmistakable. These are really significant differences. So now turning to the self-efficacy question, same general technique. Bin the students, start with one-way ANOVA, follow up with the Tukey test that says that there are significant differences in the pairs, and then look at the effect sizes. And once again, you see big differences. And I want to point out that what we've seen in our 10 bins is there are kind of 2 categories. If you look at the graph on the right, it really jumps out at you that MATLAB in general, we're asking students, are you confident with MATLAB? Are you good at MATLAB? Rate your skills on a scale of 1 to 10 in MATLAB. And their confidence just goes up and up and up as they go from the 100 to the 200 to the 300 to the 400 level. Matrix operations, on the other hand, are something that they don't see very much in the 100 and 200 level classes. But then they make a real jump once they're taking optics and quantum mechanics and things like that. So we often see that looking at the full data set. There are the skills that go up continuously and the ones that take a big jump at the 300 level. Now, you may be asking yourselves, if students aren't doing computational physics using matrix operations in the 100 and 200 level classes, why are they rating themselves a 6? And we kind of anticipated this might happen. And that's why we asked them about their prior knowledge. So on the next slide, this is just a full data set. We haven't done the ANOVA or any of the other details yet. This is just the raw stuff. And what I want to draw your attention to is sort of the broad categories here. So what we're asking them here is to estimate their initial self-efficacy versus course level. And again, the purple bars are all the 400, green is 3, red is 200, 100 level is a 1. So for something like matrix operations, when they're at the 100 level, they're rating themselves up here in the 5.5 or so range. And then as they progress through the program, their estimate of their initial skill goes down and down. Because what's happening there is they're realizing that, oh, there's a lot more to this. I thought matrix operations just meant what they taught me in the intro calculus sequence, or in that the math department has a so-called multi-dimensional math class where they learn things like how to take a determinant to do a cross product. And students are thinking, oh yeah, I know matrices, I've seen matrices before. But then as they progress through the program, they realized, no, they really didn't. And we see that a lot. I mean, look at data analysis. Again, it's going down, down, down as they become more sophisticated. Their estimate of their prior knowledge decreases. The only things where they knew they never knew anything were the ones that were really, too jargon heavy. Something like LaTeX. You ask the freshmen, how are you at LaTeX? They have no idea. They don't even know what that is. In fact, we're starting to introduce it. We have a freshman seminar that I'm teaching in collaboration with the math department, and we're starting to teach them LaTeX as freshmen, but there's just a handful of students in that seminar, and they're swamped by all the others in the intro course sequence. So that third construct, we're yet to analyze this in great detail, but that gives you a little inkling into why some of those numbers are so high, even at the outset. So with that, I want to start to wrap things up. Our department is well along the way to full integration. As Gautam mentioned, our goal that was actually stated in our IU's proposal, and that grant expires in 2023. By that time, we want to have 25% of the curriculum be computational, and that can be construed differently course by course. We've moved from small internal support to significant external support. We've developed and validated this first evaluation tool. We have established, at least moderately, that it's valid and reliable, and we see real effect sizes in affect and self-efficacy. Now, moving to the future, we want to get into a more detailed analysis of that initial self-efficacy part. I find that fascinating, the way that played out. And I want to get into that more deeply and see what kind of real conclusions we can draw. Also want to do some work on developing more detailed rubrics to evaluate those student learning goals. And the first one we want to focus on is that business of exploring the physics. Once students have gotten their code working, what are they doing? Are they really starting to think computationally, or are they viewing this as a programming task? Then we want to get them into more details about things like how they gain confidence in their code, how they test it. We have a regional workshop that we plan to offer next year. And hopefully some of you might even be able to come to that. With that, I want to thank, first of all, I want to thank Alexis, our external evaluator. I saw that she was here with her cat, Luca. I want to thank Danka Maric, who provides research assistance from our STEM Education and Innovation Research Institute. Of course, thank the folks at NSF. And I really want to thank my colleagues in physics. As Gautam mentioned, I was chair as we launched this process, and I couldn't have had a more collegial, open-minded group of people to work with through the early stages of this project. And of course, the third time through, 3 times the charm, thank PICUP once again. So thank you all. And I guess we can take questions.
Yeah, so I would thank you, clap for Andy and for Gautam. Thank you very much. If you have questions, let's go ahead and put them into the chat. And so if they accumulate, then Andy and Gautam can sort of sift through them. I have one question though to get started, and that's this. With regard to the self-efficacy, that is also fascinating to me. I'm wondering if you have any qualitative data, like actually individual interviews with students, so that you actually know that that is what's happening in some sense. Maybe getting a little finer grain data, I suppose.
So we had hoped by this time to have some of that data, but as Alexis can tell you, it's really hard to do that during a pandemic. In a normal semester, we would be able, we would have started doing this last year when the IU's funds came in. And it would have been very easy to just like grab the conference room at a time that classes were letting out, offer free pizza for physics majors to stop in and chat and form a focus group or agree to do individual interviews. But it just became too unwieldy during the pandemic. So that is something that we do intend to do, but it is not something that we've done yet.
Okay, thank you. I see that William Wolf has a nice question in the chat. I don't know if, yes, William, if you'd like to say it or if maybe expand.
No, I can read it. I mean,
all right.
William wants to, but I think it's a perfectly good, clear question. So I'll take a stab at it and maybe offer an opportunity for a deeper dive. But so there are non-majors in the introductory sequence. They're mostly engineering majors, although there are some computer science majors and some math majors just in the mechanics class, but not in the E&M class. And they don't find it a distraction. Actually, so what happens is in the introductory level class, what we've done, we don't use MATLAB. We're using Excel in the intro level class, and we're building it in as essentially a lab. So they get encouraged to use Excel to visualize functions. I've sort of shown them how to do that in lecture a few times as they do. I'm teaching mechanics at the moment, so that's where my head is going. But we also use it in the lab as a data analysis tool. And also there is one fully computational physics lab where their goal is to build a spreadsheet that just does the calculation for an object falling from a height with air resistance. And then they do some experiments within that that simulation. So they build the thing. I sort of show them there's a bit of a snippet of code that's given to them that shows them how to do the air resistance for a sphere of given radius and mass. And then they put in a calculation to do so they can vary the density and the radius. And then they can do experiments with doing things like, for instance, how does terminal velocity vary versus the radius of the sphere? And for a fixed density, it's going to vary linearly because the mass is going to go up like the cube and the air resistance is going to go up like the square of the radius. So that's something that they can explore in the lab once they've got their code working. And I coach them on how to test it, set the density of air to 0 and see if it reproduces the original result, the analytical result. So they've kind of enjoyed that, if only because it's a lab that from which they're excused from going into the crowded room. They don't have to drive to campus. And a lot of our students are commuters. So for many of them, the lab, it meets at an odd time. It's not, because of the way their schedule works, they normally don't have anything else at that time of day, any other day of the week. So often they can, if they don't have the lab, they cannot drive to campus. Well, that's an ancillary reason for liking it.
If I can just add to that.
Yeah, please.
There are some advanced courses also in which we have non-majors, in particular because our mathematics department requires their majors to have a minor, and many of them take physics as a minor. Now, the math department is not doing anything along these lines of computing. And so when those students suddenly come into our junior level courses, they're not at that background of computing. They've not come through our system. But anecdotally, and I happen to teach a couple of those courses, the students seem to appreciate this. They say, okay, because they come in being very good at sort of the analytic mathematical abilities, but then to, adding this on top of them, they think helps them to understand what they had learned in mathematics also. So it appears to be generally well received by them.
Axel Mellinger has a very nice question as well, following up William's question.
Oh yeah, on transfer students. So again, there aren't a lot, and the easy answer is on a case-by-case basis. Many students do come in with some familiarity with computing, though not necessarily with MATLAB. But it's easy enough. Gautam, you've probably had more experience with this than I have, but in my experience, students who have some background often come in ready to learn it. And they can of course take that course at any time in their program, and we'd encourage them to do it. But a lot of them are also pretty able to pick it up.
So one of the things we do, and I teach some of these courses, is our class sizes are small enough. They're say anywhere from, so I'm now talking about the sort of beyond the introductory level, there may be anywhere from 10 to 20 students. And so if I find that there is a student who has not come through our system and is not quite familiar with, say, MATLAB or computing, then we pair them up with another student who may be more facile with these things. And that has generally worked quite well. We often, we encourage our students to sort of work together, especially on the computing assignments. We in fact have some plans for studying how pair programming works and how efficient it is and how each partner in the pair contributes to the effort. So this learning from the peers seems to work reasonably well.
Thank you. There's a question from Igor from Canada asking you to please comment on your choice of MATLAB.
Yeah, that was a debate. I mean, Python was definitely a very close second. I think the main reason we chose MATLAB was because we do have a site license for it, so it's equally free. And many of our students are double majors with engineering, and they use MATLAB in their classes as well. So it was an opportunity to sort of synergize with them. And
Yeah,
also, you know, it's a job skill as well. Many of our students go into engineering careers, and they're going to see MATLAB in the workplace. Gautam, you want to expand on that?
Yeah, I just had one more thing, which is that some of our faculty were using MATLAB and were, you know, very much familiar with it. And so that made it easy. You know, if you can get a third of the faculty on board, then you're just worrying about the remaining 2/3. Whereas if you're trying to get everybody to learn something new, which Python would have been, there could have been a bigger potential barrier to. So we had faculty who were using MATLAB, and at least 2 or 3 of them were using MATLAB to do research with high school students. So we knew that high school students were able to pick up MATLAB and, you know, do some fairly sophisticated journal quality research. So we thought, since it's freely available to our students, some of our faculty already know it, they can guide the other faculty members in how to use it. And we had seen that high school students were able to pick it up fairly quickly. And so so that's how we ended up with MATLAB.
Thank you. One of the issues that Gautam, you spoke to early in the presentation was about faculty concerns about learning something new, perhaps, or maybe just the extra work of including computation. And Adam from UCF has a really good couple of questions about how were these computational activities developed, and, you know, was effort shared, or was it just the people who maybe specialized in particular courses, the main developers?
Yeah, so for those faculty who were familiar and comfortable with MATLAB and sort of had ideas on what kind of computational assignments they could come up with, they did it on their own. And I would say this was about maybe half our faculty, so maybe let's say 5 out of 10 people. For the remaining people, you know, in my slides, I said 2 faculty members in the chair worked with them. And that's essentially what we did. We went to them and said, look, you know, okay, you teach intermediate mechanics, you know, let's try to come up with some assignments that you can give to your students. So we sat down, we looked at their syllabus, you know, we said, okay, I mean, this is a nice place to maybe put in a projectile with air resistance problem, or, you know, or a visualizing the electric field due to some non-uniform distribution, you know, so just looking at their syllabus, but it required a couple of faculty members to go around to each individual faculty member and say, do you have enough to do something computational in your course? So in the first semester, you know, it was maybe just a couple of problems, 3 problems. Then in the summer, you know, sat down with them again and sort of tried to expand the portfolio of assignments that they could create. Now that we've had the program in place for about 4 years, what we're finding is that the faculty members now are able to, they have become sufficiently adept that they're able to come up with their own problems and own assignments and projects, and they have picked up enough MATLAB that everybody is pretty much independently operating now.
Can I ask a follow-up? Where do you take your notes from what a computational activity ought to look like? Right. Well, who else did you all look at to say that's what I want our, you know, air resistance or Monte Carlo activity or something to look like?
So our primary source was PICUP. I mean, that's where we keep going back to PICUP, and in case we did not thank them, we should. But once we had done that and we were sort of aware of what is out there, then we sort of simply went to various websites. There are some books on computational physics problems. I can remember early on when I first started, I went to a website for some course at the University of Rochester, and I found some very sort of very sort of interesting and fascinating problems. And they were just problems where, there was no solution, but it was clear that they could not be done analytically, but at the same time, they were the kind of things you could introduce it very early in a physics curriculum. Then I guess maybe those were the primary sources that I can think of.
Great. Thank you, Adam. So a couple more here. Troy Messina has asked, are your curricular materials going to be available on PICUP? And then Christine Washburn has asked, do you have any sense for how often students copy each other's code rather than write their own?
Yeah, so on the first question, are your materials going to be available on PICUP? The answer is slowly. So what we have done, I think, is so far we have put 2 assignments on there, and one in E&M, one in mechanics, and then we have another one that's on nonlinear dynamics that's in the work. I think that part has been a little bit difficult to get. What we want to do is we want these faculty who are developing the assignments to put their assignments on PICUP. Mm-hmm. That has been, again, there's a potential barrier here because PICUP has a very the exercise sets have a very specific format, and people just have to sort of get used to the idea that this is how I need to write things for this particular site. When we ask them, they say, yeah, this summer that'll be at the top of my list, but the summer comes and goes, and then but yes, the intention is there. The other question, how we have a sense of how often students write their own code. So we are under the impression that they write their own code. We have not systematically tested this in every single course, but what we do is we stress to the students that, look, each person writes code in a different way. The logic, the flow, how there's 50 different ways of writing it, and that whatever your classmates may be doing could be incorrect. So don't copy each other's code. And I can tell you myself, from my own experience, I teach 2 of these courses at the 300 level. The students seem to be writing code independently, and my colleagues also tell me in their courses they think the students are doing it independently because some students just don't get the right results, whereas the others do. And people get in between, all the way from the perfect results to the perfectly incorrect results to something that works part way, and then they're constantly in touch with the instructors that their code is not working. And again, because we only teach anywhere from 10 to 15 students in any of our upper level courses, we have a fairly good handle on what they're doing.
Okay, thank you. I think we have one last question from Alexis, your external evaluator. Is there any incentive for faculty to put things on the faculty commons or the peer-reviewed part of the PICUP website?
So not from us, other than the general sense of having, okay, there's the peer-reviewed part at least is a legitimate publication. I mean, certainly when I was chair, I was giving people appropriate chairly pats on the back for putting that kind of activity in their annual review. But I mean, there's no major incentive from us. We didn't build that into the grant, for instance.
Okay, thanks very much for the answers. And I guess out of respect for people's time, I think we're trying to wind it up after about an hour here. And so one more time, I'd like to ask everybody to give some virtual applause and thanks to Andy and Gautam for a very lovely presentation. And I'm sure they would welcome anybody to go ahead and contact them, by email if you have questions that come to your mind later, or if you are interested in their materials and maybe the survey, which Andy has certainly indicated they would share. So I think this brings the webinar to a close. If anybody wants to hang out for a minute or two, I'll be here and going to try to end the recording if it hasn't already. And thanks everybody for coming. I know it's an evening hour, and just thank you for coming.
Thank you all for your attention.
Yeah, Gautam and Andy, thanks for coming out.
Oh, our pleasure, Kelly. Thanks.
Yeah, you bet. And also, when you get around to thinking about this workshop, you know, we'll advertise it to the extent you'd like it to be advertised, or get the word out, or whatever. So
Sure.
make sure you keep us in the loop on that.
Absolutely. No, we wouldn't miss that opportunity.
Yeah. You're
And
gonna
thank
do it.
Also for the invitation.
What's that?
No, I was just saying thanks to Ernie for
Oh, yeah.
this opportunity to present.
My pleasure. I mean, since seeing what you were doing back in the event that Alexis and Tim organized in the spring, I thought this is a natural. So thank you very much for taking the time to do this. Really appreciate it.
Ernie, did you deliberately wear the pickup polo for this?
You bet I did. That's what it's for, is for pickup events. You got it. So I'm representing. There's my pop.
Yes, I can see that.
Thank you, everybody. Thank you very much.
Yep.